We're now ready to study collisions in its full glory. Okay, we have all the pieces. We know about energies, we know about momentum conservation, and we're now ready to discuss collisions. Okay, but in order to do this, we're going to classify collisions into two categories. We're going to call them elastic and inelastic collision, and the way collisions are classified is going to be based on their kinetic energy conservation. So collisions are classified based on kinetic energy conservation. Now remember, this is kinetic energy conservation, okay? Not mechanical, not momentum, nothing else. It is very clear. It is kinetic energy conservation. This is where people make a lot of mistakes. They forget about the fact that it's kinetic energy, and then they think it's mechanical and momentum and all that. So very clear, collisions are classified based on kinetic energy conservation, which means by conservation we mean that whether it's going to remain fixed or no. Okay, so let's look at the two ways. If Ke is conserved, which means if the kinetic energy before a collision is equal to the kinetic energy after a collision, then the collision is elastic. Okay, now if Ke is not conserved, which means that the kinetic energy before the collision is not equal to the kinetic energy after the collision, then the collision is inelastic. Great. So now that we have our two collisions, okay, elastic and inelastic, let's explore each kind and let us see what we need to do. So what we'll do is we'll study inelastic collision first. It's a little easier to deal with. Elastic collision is a little involved. There's a lot of calculations and all that involved in it. So let us focus on inelastic collision. In fact, we've already looked at a couple of inelastic collisions. In fact, the two problems that we have with the two people push each other off, and then also the problem with the ballistic pendulum, they're both examples of an inelastic collision. And in each of those two cases, if we were to calculate the kinetic energy before and after, we would see that they are not equal to each other, and that is basically what implies that the collision is inelastic. In fact, they were even perfectly inelastic collisions. Okay, so let us study inelastic collision first. Okay, so the criteria for a collision to be inelastic is that KEI is not equal to KEF. Now, in problems, sometimes, most of the times you will not be told whether a collision is inelastic or not. It's something, one of the questions could be, hey, is the collision elastic? Is it inelastic? So you cannot assume kinetic energy conservation. Now, that's one thing that you must keep in mind. If you are not told about the collision, whether it's elastic or inelastic, please make sure that you do not assume kinetic energy conservation. Okay, so of course we ask the question, in an inelastic collision, what can we use? All right, so let us first look at just a head-on collision, and later on we look at glancing collisions also. A head-on collision simply means everything's happening in one dimension. That means two objects, they come towards each other. So if I have a block moving to the right, let's say I have a block of mass m1 moving to the right with speed v1, and let's say I have another block of mass m2 also moving to the right with speed v2, or could be moving to the left, doesn't matter, and let's assume v1 is greater than v2, and they collide, and after the collision they both continue to move in the same direction. Okay, so let's say that after the collision, m1 is moving in this direction, let's call it v1f, and m2 on the other hand is moving in this direction with, say, v2f. Okay, and we can use momentum conservation. We have to figure out what we're going to use to obtain the velocities. Okay, so what we know is, once again, that in the collision, the two objects are going to exert forces on each other. So let's say that, right when they're colliding with each other. Okay, so this is m1, m2. m1 is exerting a force on m2, and m2 is exerting another force on m1. These forces, as you've probably already recognized, are going to be equal and opposite. And in that case, what we know is again that the net external force is going to be 0, and as a result we can use momentum conservation in these collisions. So we can use Pi equal to Pf, and once we know Pi equal to Pf, we can use this to figure out the final velocities. Okay, so we have a head-on collision, and we can use or rather a head-on inelastic collision where the kinetic energy is going to change before, it's going to be different before and after the collision. But one thing we can do is we can use Pi equals Pf, okay, assuming again of course that that the net external force is 0. So let us apply this to some situations and let us see what we can do. Okay, so first what we'll do is we'll look at a subcategory of inelastic collisions, which is just a perfectly inelastic collision. And this simply means that objects stick after the collision or were stuck before an explosion. Okay, so objects will stick after a collision or were stuck before an explosion. Now we've already seen examples of each kind. Okay, objects sticking after the collision was a ballistic pendulum, and objects being stuck before an explosion were the two ice skaters who pushed each other off. They were together, they were one unit, they pushed each other off, and they move in opposite directions. Okay, so they are both examples of perfectly inelastic collisions. Now, let's do a simple example here, and let's figure out something. So let's say that I have a bullet of mass m moving to the right with speed v, and let us say that I have a block of mass capital M at rest. Okay, and let us say that the bullet gets embedded in the block, and after the collision they move as one unit, okay, to the right, and our goal is to find the final speed v final, and also to find the change in the kinetic energy. So let's do that as well in the simple quick problem. Now we know that there are no external forces. We do not know, let's assume that we do not know whether the kinetic energy is fixed or not. Okay, but let's try to figure this out. Let's try to apply what we know is, since the net external force is 0, we can use Pi equal to Pf and obtain the result. So since momentum in the beginning is simply equal to mv, and since they move as a unit, momentum at the end is m plus capital M times v final, what we know is that the final velocity is mv over m plus capital M. Alright, great. So we figured out what our final velocity is. Let us also find the change in the kinetic energy. So delta Ke is going to be equal to Kef minus Kei. Now in the end, since they are moving as one unit, the kinetic energy is 1/2 m plus capital M times Vf square, but Vf is nothing but mv times m plus capital M square minus the initial momentum. And in the beginning only the bullet is moving, the block is not going anywhere. So let's simplify this. So we have 1/2 m, actually the one of the m plus m's cancels out, and we have m square v square over m plus capital M minus 1/2 m v square. Alright, let's factor out 1/2 m v square, and then we have m over m plus capital M minus 1, and this becomes equal to 1/2 m v square. So we can factor this out and get m minus, actually we can multiply and divide the second term by m plus m. I get m plus capital M, and what we know is that this is equal to 1/2 mv square times minus capital M over m plus m, and this is equal to minus 1/2 m times capital M v square over m plus m. Now the negative sign here implies that energy has been lost. Okay, so keep that in mind. What it says is that in the beginning the bullet had a lot of energy. In the collision, this energy was lost Okay, so loss of kinetic energy, it was lost, and what happens essentially is that this energy goes in the form of heat. Like if you were to touch the black bullet after the collision, you'd see that it is warmer than what it was before the collision. Okay, so this is an example of an inelastic collision or rather of a perfectly inelastic collision. So once again, the key concept here to keep in mind is that we have collisions, we classify them based on kinetic energy conservation. If kinetic energy is conserved, the collision is elastic. If it is not conserved, then it is inelastic. And then we did an example of an inelastic collision. Okay, so let's take another example of an inelastic in the next one, and then we will try to figure out how to deal with elastic collision.